Hello, let us try to integrate the absolute value of x. And the absolute value of x really is the same thing as just plain x, except that if x is smaller than 0, then you take minus x instead. You can compare the graphs for the functions. I mean, the absolute value of x and x are the same thing, but this part here, where x is smaller than 0, is flipped around the x-axis. So the strategy to integrate this is really easy. I mean, can't we just take the normal integral of x, which is a half x squared, and then flip this part here where x is negative, where x is negative, less than 0, can't we just flip that part around the x-axis as well? By which I mean multiply it by minus 1. So let us sum this up. What our strategy here is in general. Our idea is basically the following. So if f is any function, then I mean the absolute value of f of x is just plain f of x if f of x is greater than or equal 0, but it's minus f of x if f of x is less than 0. And I mean the integral of minus f of x is just minus the integral of f of x. And so our idea, what we assume is that the integral of the absolute value of f of x is just normal f of x if f of x is greater than or equal 0, and it's suddenly minus the integral of f of x if f of x is less than 0, which makes sense graphically, as I've said. I mean, if you flip a function around the x-axis or multiply by minus 1, then its derivative is also flipped around the x-axis or multiplied by minus 1, right? I mean, if the function is rising and you multiply it by minus 1, then it's suddenly falling. But of course, it's falling at the same rate of change. So the derivative doesn't change, but only the sign of the derivative changes. And because of that, this also works vice versa when you look at the integral or the antiderivative. So this is our strategy here. And in our case, of course, f of x is just simply x, right? And as I've already said, the integral of x is just 1/2 x squared. Therefore, we assume that the integral of the absolute value of x is just normal 1/2 x squared if f of x is greater than or equal 0, by which I really mean if x is greater than or equal 0. As I've already said, f of x is x here now. I typed this wrong, but yeah. Let's ignore that, and it's minus 1/2 x squared if x is less than 0. F of x is equal x. Let's remember that, because here it's again says if f of x is less than 0. So that's just the basic strategy that we are doing. And so we define capital F of x to be 1/2 x squared if, again, it should be if x is greater than or equal 0, but it still is correct because now we said that f of x is equal to x. Although technically it should here be a defined as, f of x defined as x, like here. Capital F of x is defined as this thing here. And yes, and it's minus 1/2 x squared if x is less than 0. This is the function that we believe to be the antiderivative for the absolute value of x. And now we will continue up here, so we will now need to get rid of the graph for absolute value of x because it's getting in the way. And so what we have to do is we have to show that this capital F is differentiable and that its derivative is the absolute value of x, right? That's exactly what you have to do to show that something is the integral of something. And first we just note that we can write this right here more beautifully. I always don't like it to write a function with a big bracket and then do a case consideration, you know. In one case, x is greater than or equal 0, and then in the other case, x is smaller than 0. I don't like that. I don't like to have to differ between two different cases. I want to write this without those brackets. So let us look at that. I mean, this is basically, this capital F is really just 1/2 x squared. Basically, how I thought of it as a kid, I wanted to say, when I was in school, I always thought that it was just 1/2 x squared multiplied by absolute value of x divided by x. Or, which is actually more intuitive, I guess, and that's why I've written it like this here, is that you multiply it by the sign of x. But of course, the sine of x is just equal to the absolute value of x divided by x. So yes, this here can be rewritten as simply the sine of x times 1/2 x squared, right? Because what you do is, this function is 1/2 x squared, but whenever x is less than 0, you multiply it by -1, which is really just the sine of x, right? You multiply this by the sine of x, as it says here. But yes, the sine of x is just the absolute value of x divided by x, and also the other way around. It's also x divided by the absolute value of x. But writing it like this is more useful, because if we write it like this, then this x squared and this x cancel, and we are just left with x times the absolute value of x divided by 2. And if we want to differentiate this function, then we need to be careful. We can't just take the derivative like normal, because the absolute value of x isn't differentiable everywhere, but we will try to make it as easy as possible. And the first thing we do is we basically cheat, because we basically use a very standard argument. What we're saying here is, okay, so this is just x times the absolute value of x divided by 2. And really, this is just a product of functions which are differentiable for x is not equal to 0, right? Hence, for x is not equal to 0, capital F is differentiable as a product of functions that are differentiable for x is not equal to 0. That's exactly what I've just said. X is differentiable for x is not equal to 0, and the absolute value of x divided by 2 is also differentiable for x is not equal to 0. And so we get, if x is strictly greater than 0, holy shit, why the hell does this greater than sign look so fucked up? I just realized that. Well, whatever. If x is greater than 0, then capital F of x really is just 1/2 x squared, and capital F prime of x is equal to x, which is absolute value of x, which is exactly what we want. And analogously, if x is less than is strictly less than 0, then capital F of x is -1/2 x squared, and f prime of x is minus x. But this is also the absolute value of x, if x is less than equal to I'm sorry, let's try this again. So if x is less than 0, then capital F prime of x is minus x, and that is just the absolute value of x if x is less than 0. So this is the easy case. You basically just use the standard argument. You basically, for the easy cases, you always say, oh, you have a composition of differentiable functions, or in this case, a product of differentiable functions. And so this is really easy. And finally, we need to show that capital F is differentiable at 0 with capital F prime of 0 equals 0. But since the absolute value of x is not differentiable at 0, we cannot argue that capital F is differentiable at 0 as a product of differentiable functions at 0. We have to really take a look at the differential quotient here and show that the limit of the differential quotient exists for x is equal to 0. And in order to do this, we note one thing first. And what we do note is that capital F of x is continuous, which is of course mandatory. I mean, differentiability implies continuity. So if this function really is differentiable, then it has to be continuous. And this is in fact continuous everywhere. And again, it's a very easy argument. We first notice capital F is continuous as a product of the continuous functions x and absolute value of x divided by 2. These two functions here are continuous everywhere, even at 0. And so capital F is continuous everywhere. In particular, capital F is continuous at 0. Hence, it suffices to consider the left-sided limit of the differential quotient and right-sided limit of the differential quotient for capital F at x is equal to 0. And that strategy only works for continuous functions, you know, to take the left-sided and right-sided limit of the differential quotient. There's this famous counter example, which I'm going to give. One needs continuity for this strategy. For example, the sine of x is not differentiable at x is equal to 0, even although the left-sided limit and right-sided limit for the differential quotient of the sine of x both exist and are equal to 0. Yeah, here, if you draw the sine of x, you can clearly see this function never changes. It doesn't have any rate of change. And yeah, the rate of change as x approaches 0 clearly approaches 0 both from the right here and from the left here. But still, this function is not differentiable because it's not continuous here, which is a pretty technical reason. If you look at the proof for differentiability implies continuity, then you just simply see that in order for the limit of the differential quotient to exist, you need at some point that the limit of the function itself exists, which just means that the function is differentiable. Okay, so that's just a minor little note here. And so, yeah, but since this function is continuous, we can apply the strategy with the right-sided and left-sided limit. And we look at the right-sided limit first of the differential quotient. The limit as x approaches 0 from the right of capital F of x minus capital F of 0 divided by x minus 0 is equal to the limit as x approaches 0 from the right of simply x squared divided by 2 minus 0 divided by x minus 0. Why is that? Well, because we are now approaching 0 from the right, which means we are always bigger than 0. And if we are bigger than 0, if x is if x is greater than 0, then capital F of x is just always equal to 1/2 x squared. So we can just plug 1/2 x squared here, and what we see here, this limit here, is really just the derivative of x squared divided by 2 evaluated at 0, which I've noted here as x squared divided by 2 prime evaluated at 0, and that's equal to 0. The same exact argument holds if we approach 0 from the left. There we then get that capital F is just minus x squared divided by 2, and then we get minus x squared divided by 2 prime of 0, which is also 0, and so we are done. We've shown that capital F is differentiable because these limits here coincide, and these two limits are equal to 0, hence capital F prime of 0 is equal to 0, which is exactly what we did. And since we've already shown that the derivative for capital F is correct for any x that doesn't equal to 0, we are done. In total, capital F is differentiable with capital F prime of x is equal to the absolute value of x, and so the integral of the absolute value of x dx is just x times the absolute value of x divided by 2. And if we draw all of these things again, let us get rid of all those text boxes here to the right so that we can see the graphs for the functions better. Then we can see, holy shit, that's a lot of text. We see here the absolute value of x, and here we now see 1/2 x times the absolute value of x, you know, this function here. And this is really, as we can see here, this is just 1/2 x squared, but it's flipped around the x-axis here for x is less than 0. You know, basically 1/2 x squared is multiplied by -1 whenever x is less than 0, and so we get this green function here. And then let me delete this magenta function, go to this green function and add the derivative dy dx, and we add it in magenta. Then we see we do get the absolute value of x, right? This red and magenta function coincide. And if we look at we click on calculate here, and then we click on table for this purple function for the derivative of our capital F, which was x times absolute value of x divided by 2. If you look at the values, then you see that it's defined everywhere, and even at x is equal to 0 here. At 0 it equals 0, this green graph, and so we are all right. And vice versa, if we check now the table for the green function for x times absolute value of x divided by 2, and then we check here the tables, then we see that this green function, x times absolute value of x divided by 2, is differentiable everywhere. Here f prime exists everywhere, and f prime of 0 here is equal to 0. Yes, so everything is absolutely correct, and we successfully integrated the absolute value of x, and we are done. Hope you liked this, and I will see you guys in the next video.